Okay, we'll get started. So before the talk, I want to say a few things. First, we have established a Slack channel where the participants could discuss, and also you probably already received the invitation to that. So please join those Slack channels, and also please post your posters. If you're going to present the poster, please put those in the Slack channel as well. There's subgroups for each poster sessions. And also, please also email your poster to our new email account, psccm@princeton.edu. Our previous summer school email accounts have some problems, so we kind of switched to a new email account to contact those summer school issues. So that will be it, and we'll have a poster session right after this talk. Yeah, let's have Professor Yacoby tell us more about Magnons in quantum materials.
Great, so let me share my screen again. Okay. So just a short recap on the previous talk. So in the previous talk, I discussed a new mechanism for launching and detecting Magnon's neutral excitation in quantum Hall systems. And essentially during the second part of the talk, we discussed an experiment that looks like a scattering platform, where here on the left-hand side of the sample, we're generating Magnons. We have in the red region in the middle, the red box here indicating a region where it's kind of a test region. We're probing whether Magnons can propagate across this region or not. And if they can, those Magnons that arrive on the other side would lead to a signal that we can detect non-locally at contacts 4 and 5. So this is already kind of a simple version of what I call a scattering platform. It's basically like a transmission experiment where we can monitor whether Magnons can propagate through this region and how effectively can they propagate. And I think there's much more work to do in this domain, but what I'd like to do now is kind of broaden the scope and ask, to what extent can we generalize this? So what do we know about scattering platforms? So generally, a scattering platform is a system, if you consider, for example, X-ray scattering or neutron scattering, we have a source of particles like waves, X-rays or neutrons. They're propagating in an unperturbed medium. We generate them with a well-defined energy and wave vector. And then these particles impinge on a sample and they undergo a specific interaction characterized by what we know as the structure factor. And then they scatter off into space again, where we can put our detectors. And by monitoring the signal that arrives at our detectors, both spatially resolved, we can basically learn something about the target itself. And there are several appealing things about it. First of all, it's an energy and momentum resolved experiment. Second, we don't really need to probe the properties of the sample where the interaction happens. The nice thing is that in the scattering process, we're monitoring what's happening very far away from the sample, where we have only free particles, and yet we can reconstruct some property of the target from learning about the spatial dependence of the scattering problem. So the goal of this talk today would be to build up towards what I call is a Magnon scattering platform, where the impinging particles are now going to be Magnons. We're going to strive to generate Magnons with well-defined energy and momentum. We're going to have these Magnons interact with the target and then scatter off into, again, vacuum, effectively vacuum, whatever medium that they can propagate unperturbed. And then we're going to detect them and see whether we can reconstruct the properties of the target. So roughly the outline for today's talk, in order to construct all the components, there are going to be 3 parts to this talk. First, it's going to be how we detect magnons using nitrogen vacancy center magnetometers. So we're going to move away from graphene at this point. We're going to be talking about other mesoscopic systems, and you'll hear more about what our target is. But the point is that we're going to be using an external probe this time, not something that is specific to a particular material system like we did with our magnons and quantum Hall ferromagnets. This is kind of a more generic platform. It's a scanning magnetometer, so it allows us to measure magnetic fields in space. So I'm going to spend some time describing what is the connection between our ability to measure magnetic field at different frequencies and magnetization, which is basically the property described by the magnons. I'll then give a few examples of how these NV centers measure magnons. So I'll talk about measuring thermal magnons in a magnetic insulator, and actually show that by doing this kind of measurement, we can extract spin chemical potentials in the system and really see also some indications or results that are consistent with Bose-Einstein condensation of magnetic excitations. And lastly, we're going to have all the ingredients that are needed in order to describe the Magnon scattering platform. So I'll show some results on and you can see it in the bottom panel here, an image of a scattering map of magnons off a target, and our efforts to use the scattered magnons to reconstruct the properties of the target. So generally speaking, our goal is to really build up towards this type of experiment. What you can see here is a thin slab. This is going to be a magnetic insulator. That's going to serve as our vacuum. It's vacuum in the sense that magnetic excitations, magnons, can live very long in this medium. They're very weakly damped. This is YIG, yttrium iron garnet. It's kind of the holy grail of high quality magnetic material. We're going to launch magnons using these strip lines on the left, these yellow lines. And what you see here is an NV center cantilever that will image the real space patterns of magnetic fields and will extract what the magnetization density at any given point, its time-dependent component, and see how a target here shown with a small disk in the middle behaves. And our goal here, you'll see really kind of our first step towards realizing this magnetic platform, but I think our vision is that we can then replace this target with any type of material. And again, the fact that it's small is not going to be a problem because we're not going to be imaging directly over the material. We're going to be imaging far away after the magnons have scattered to learn something about the target itself. So generally what we'll need is to demonstrate that we can launch coherent waves with well-defined energy and momentum. This is something that in the magnetism community has already been demonstrated, but we'll show that we can do it also while detecting things with NV centers. We want to show that we can detect both the amplitude and phase of the scattered waves. This is really important. In most scattering experiments, if you think about neutron or X-ray scattering, what you're measuring is an amplitude. You lose the phase information. Here you'll see that we can actually measure both amplitude and phase of scattered waves, which in principle then should allow us to really reconstruct without any unknowns what the target is. But as you'll see, there are kind of complications with that, and it's going to take some time to really perfect this. 3, we want to demonstrate that when we put the target material on top of this scattering platform, that there is an appreciable interaction between our impinging particles, these magnons with well-defined energy and momentum, and our target material. And finally, we'd like to see if we can get reliable extraction of target material properties by measuring the scattered waves. So this will be kind of the program of the last third of the talk when we actually combine everything to form this scattering platform. All right, so since our tool for detecting these magnons in YIG, in this magnetic insulators, NV centers, I wanted to give a brief introduction to the properties of NV centers and what it is that they're really measuring and how. So NV centers are basically defects in diamond. They consist of a substitutional atom, a nitrogen, and a vacancy, a missing carbon atom. so this defect has an axis, the NV axis, and in principle, it's measuring magnetic field. The easiest application is to measure magnetic field along this axis. The underlying energy, basically the underlying energetics of this defect is shown here. It's a 3-level system. At 0 magnetic field, it consists of an MS equals 0 state and an excited MS equals ±1 state that are degenerate, separated by roughly 3 gigahertz, so much smaller than room temperature. But as you apply a magnetic field, the excited states split, and if you choose any two, let's say the MS equals 0 state and the MS equals -1 state, you form a 2-level system that basically behaves very much like a natural spin. It has a G factor of 2. And you can think of it as a controllable spin. One of the really attractive features of these NV centers is that they, you can detect the spin state, namely whether the electron is in its ground state or excited state, simply by monitoring the fluorescence of the system. If it's an excited state, it turns out that the fluorescence, when you shine green light on this defect, it emits in the red, and the number of photons that are emitted is smaller when it's in its excited state relative to the ground state. Another very attractive feature is that after you shine it with green light for some time, more than a microsecond, the system eventually relaxes down to the ground state. So even though this energy separation here, 3 gigahertz, is much lower than room temperature, you can really initialize the system into its ground state with very, very high fidelity, even at room temperature, by pumping it with this with green light. By the way, the entire previous talk was done at dilution temperatures. The entire talk today, this talk, is going to be all at room temperature. Another attractive feature, of course, is that this mechanism, this diamond defect and its behavior in response to light magnetic field, is completely unaltered when you change its temperature. So this technique is operational from millikelvin up to very large temperatures above room temperature. And of course, I'll talk about spatial resolution a little bit later, but ultimately you can imagine that one limit to the spatial resolution is going to be the distance of the NV from the object that you're trying to see. And so because the intrinsic size of this defect is atomic, in principle, its spatial resolution is atomic, but it's going to be limited by other factors that I'll mention a little bit later. So what are the modalities and how do we measure magnetic field with this defect? Well, the simplest thing is, for example, to suppose you have a finite magnetic field. And this means that you're at some value on the upper left panel here. And there are two possible transitions that you can induce by shining microwaves onto the system. The microwaves will want, basically it's an oscillating magnetic field that will want to cause transitions between the ground state, the initial state, and one of the excited states. So if you're at a fixed magnetic field and you just scan the frequency, as you can see here in the bottom left panel, when you scan the frequency, nothing happens if that frequency, the energy that you're supplying, is off resonance between the MS equals 0 and let's say the MS equals -1 state. But once you hit the resonance, suddenly you're beginning to occupy the excited state. And since the fluorescence in the excited state is lower than that in the ground state, you get a drop in fluorescence. And what this bottom left panel shows is a scan as a function of frequency, and you indeed see a lower number of photons per unit time emitted from this defect at a frequency that precisely corresponds to the magnetic field that dictates the energy separation between the ground and excited state. So now by reading off this frequency, you can determine what magnetic field it is. And here you see a frequency of 2 gigahertz corresponds to 29 millitesla. And this very simple approach provides a sensitivity in magnetic field that is on the order of a microtesla. Now, so just to give you a sense of whether this is very sensitive or not, if you have one electron spin, that's a magnetic dipole, it's generating magnetic fields in space, and you ask, well, what is the magnetic field generated by this dipole a distance 10 nanometers away from it? Well, that is 1 microtesla. So the magnetic field generated by one electron spin at a distance of 10 nanometers is about 1 microtesla, which is the sensitivity that you can get by operating this defect by this method. And this is called ESR technique. And this is applicable at very low frequencies. So here on the upper right, you see the spectral density. So what is the sensitivity of basically of the magnetic field fluctuations that we can detect? And for very low frequencies, we'll use this technique, and we can detect that with a sensitivity of about 10 to the minus 6 Tesla per root Hertz. Now, you can, of course, use this center in a much more clever way. And it's called quantum sensing simply because you use quantum techniques to control this defect. And so imagine that I have this defect and I describe it as a two-level system. And so it's characterized by this block sphere. So any superposition of its states, the ground state and the excited state, let's say the 0 and 1 state, is captured by this block sphere. If I have the ability to initialize, and we do with the green light, we can control using microwaves and we can detect by the fluorescence, then we can do much, much better than this DC magnetometry that I just described. So the way you do it is you'd initialize the spin along the North Pole, that's the 0 state, and then we'll use our control technique, some microwave at the correct frequency to tilt the spin into the equator. So we've created this state of 0 plus 1, and now we let the state evolve for some time in an unknown external magnetic field. That is, which means that we're going to acquire a phase, this phase here. And the maximum amount of phase that we can acquire is given by the total external magnetic field times the time that we can evolve while maintaining coherence. So that's this parameter T2. So that would be the signal, because later on we're going to measure this phase by projecting back the spin onto the z-axis and seeing what the fluorescence is. We need to compare the signal here, phi max, our maximum signal, to the noise. And the noise, because this is a quantum measurement, is always going to be limited roughly by pi. We'll have maximum uncertainty. But we can improve on it by repeated measurement, and that improves the square root n. And so when you combine these two to figure out what signal can you detect, you see that it goes as 1 over T2, this coherence time, and 1 over the square root of the number of measurements. And if you put in some typical numbers for NV centers, you see that you can actually get down to 10 nanotesla per 1 second integration if the coherence is of order 100 microseconds, and this is very typical. So 10 nanotesla is a much kind of 100 times better than what I described before. And it's not only that you can detect slow varying magnetic fields this way, you can actually detect time varying magnetic fields, because up to now, we've initialized in 0, we've projected onto the equator on the left panel here, left block sphere, and then we evolved for some time until we acquired phi 1, and then we measured. But if we do not measure, but we actually do a pi pulse, so we flip the spin from phi 1 to the other side here, and we let the system evolve some more, what's going to happen is that we're going to undo all the evolution that has to do with a DC magnetic field. So we're not going to be sensitive anymore to DC magnetic fields by doing this control sequence. But now, if we also flip the sign of the magnetic field we're trying to measure, as shown in the bottom graph of B as a function of time, well, the sign of magnetic field flips precisely when we do our pi pulse. Now we're going to continue to accumulate more phase after this pi pulse. And so this pulse sequence would allow us to measure AC magnetic fields. And in principle, we can engineer our pulse control sequence to extract and to filter out any section of a magnetic field spectrum that we desire. So initially, I talked about this ESR technique, which measures the very low frequency part. These pulse techniques are actually very effective in measuring magnetic fields with frequencies in the range of megahertz, because we can control our pulses with nanosecond timescales. And so this leaves a good separation between the pulse control and the evolution due to the external magnetic field. And so we can extract really portions of the spectrum at will. Now, if we wanted to go to even higher frequencies in the range of gigahertz, which is what typically happens in magnets, then there are several techniques that are available there as well. One would be just to look at spin relaxation. So if we were to initialize our NV center, let's say in the ground state, and we were to just wait, what's going to happen is that if there is noise in the system at a frequency that precisely matches the energy separation between the levels, that's going to drive this NV center and would basically relax its state from its initial state, and you'll find a finite occupation in one of the excited states. And what you see here is you can start from the ms equals 0 state and it will relax, or from any of the ms equals -1 or +1 states. And by analyzing the relaxation rate, we can determine precisely what is the fluctuating magnetic fields at these frequencies corresponding to these energy level separation, and that's in the gigahertz range. So you see that by using different techniques, we can really extract everything we want about a spectrum of magnetic field, all the way from very, very low frequencies up to several gigahertz. And in fact, we can even detect signals at these high frequencies that are not noise, and this will be very effective from our scattering platform, where there, if we have a coherent signal that we want to detect, it's going to cause not only decay, but oscillation. So it's going to lead to transitions from the ground state to one of the excited states. But if we continue to apply this excitation, it's going to take us back to the ground state, etc. So we can even measure coherent signals and how well they're coherent at these gigahertz frequency range.
Amir Yacoby, we have a question from Chunli Huang. Can you measure the Magnon lifetime in quantum Hall ferromagnets?
Right. So unfortunately, we have not applied NV centers as a method of measuring magnons. And the reason is it has to do with what I mentioned in the previous talk, and that is that the magnetization density in the quantum Hall regime is very, very small. So that's number one. Now, you could say, well, we can measure easily the magnetic field generated by one electron. In principle, we should be able to detect the signal associated with the magnetic field with the magnetization of a quantum Hall ferromagnet. But the signals are going to be weak. So it's a little bit challenging, but in principle possible. The second challenge has to do with the frequency. So I didn't mention it, but the previous talk was all around magnetic fields of several Tesla, let's say 5 to 12 Tesla. The Magnon frequency at 10 Tesla is 280 gigahertz. So it's not a few gigahertz, it's a few hundred gigahertz, and the NV center struggles to measure at these frequencies. It's not that the NV center struggles. Basically, if we needed to operate this technique at several hundred gigahertz, it makes it extremely challenging, especially if we want to be able to control, let's say, prepare superposition states, etc. So the fact that it pushes up to very, very high frequencies is also challenging. Lifetime is definitely possible, because for lifetime, we only need to initialize, and we know how to do this optically, even at very large magnetic fields. And we then wait some time. And if the energy separation of the NV center is 280 gigahertz, then at 10 Tesla, if we have magnetic noise due to our ferromagnet, we should see relaxation. So this would be a fun experiment to try. Not an easy one, but not one that we have done yet.
Okay, thank you. Another question from Anna Marija, I'm not sure how to pronounce it. What about covering the range of intermediate frequency between the static field and nuclear spins?
Well, so yes, there is kind of there are techniques. I didn't cover all the methods that allows you. I've shown a gap here because the static fields correspond to everything up to, let's say, 10 or 100 hertz. In principle, you can do. The pulse techniques really depend, how low you can go in frequency really depends on the coherence of the NV center. If you have an NV center that has a coherence which is a millisecond, then you can go down to kilohertz frequencies. So it really depends on the property of the NB centers, and you can find NB centers that will allow you to do it down to very low frequencies. In fact, there are even pulse techniques that people have been using to measure nuclear spins with NB centers where you can get frequency selectivity of microhertz. So really fantastic. And you can ask how this is possible. I don't have time to talk about it, but they're really beautiful developments in this. Also, between the few gigahertz to few megahertz regime, there are different techniques that are being used, such as T1 row techniques. Basically, these are relaxation methods of measuring the relaxation of the NB center, but not in its lab frame, but in a rotating frame. So there, this field is extremely rich, and there have been really tremendous and beautiful, innovative ideas of how to cover very effectively nearly every component of the spectrum.
Thank you. There's more question popping up, but we will save those to the end.
Okay. I'm glad there are questions, always good. So for our experiments, we want to do a scanning experiment. So I want to just give you a little bit of a flavor how we do this. So the idea is we'd like to have one of these defects very close to the surface of a scan probe tip. And eventually we ended up fabricating tips that are completely made out of diamond. They're monolithic. And we pattern them in a microfabrication fab at Harvard to have this cantilever shape and a pillar at the end. This is all one piece of diamond that has been thinned down and removed the material to leave one pillar. And at the end of this pillar sits one NB center, about 10 nanometers from the end. And the light that it emits is guided by the pillar structure, which helps our signal to noise. So the tip itself serves two purposes. One is as the lowest point in our scan probe system. So basically it's like an AFM. And the second is to guide the light out, which increases our signal to noise. And I have some details about the fabrication that if people are interested, I can talk about more towards the end. Recently, we've transitioned from this left very thin cantilevers to much thicker cantilevers on the right. You can see on the right a very thick slab, about 30 microns. And at the end, which is just the image below it, you can see the pillar hanging out. So this requires far less fabrication and makes these tips much, much easier to make. Moreover, we now have, if you look at the left, A, B, C, D, E, A, B, C, D, we have very good control over the taper of the pillar. So we can now control the angle, and we optimize this angle to extract light from the tip. And lastly, because this is a scan probe, we're moving this tip around. We want that the RF signal that controls this NB center is always to be constant. We are now integrating the RF signal with the probe itself, as you can see in the bottom two panels. So these are some of the recent kind of technical developments that we are implementing in order to make our technique more approachable. So just a few examples. I've mentioned already our ability to measure a single electron spin. Here is an image actually on the bottom, on the top right, is the image of a magnetic field generated by one electron spin. This was done at a distance of 50 nanometers from the target spin. And I don't have time to go into the details, but I mentioned that our signal to noise is 1 at a distance of 10 nanometers. It turns out that the signal to noise scales as the distance to the 6th power. So it's 5 to the power 6, which we lose by going to 50 nanometers. So here each pixel was measured 40 minutes in order to get a signal to noise of order 4. But nonetheless, we can reproduce an image of the electron spin magnetic field. And I just want to comment that when these results came out in 2013, the only previous measurement of a magnetic field from a single spin was done using magnetic force resonance microscopy by Dan Rugar at IBM Almaden, and they measured each pixel for 13 hours. So this is kind of, even though this is still rather slow because the distance is large, it is a big improvement. I talked already a little bit about spatial resolution, and I mentioned that, hey, in principle, one is limited to a spatial resolution given by the distance of the NB from the target. So here on the upper right, you see some random spins on the surface, and we have a detector, our NB center, and we'd like to detect them. It turns out that if you're trying to measure paramagnetic spins, namely uncorrelated spins, non-interacting spins, the spatial resolution has nothing to do with the distance. You can immediately understand that by thinking of an MRI system where the magnetic coils that pick up the RF signal the nuclear spins are producing are sitting maybe a meter away, and yet you get spatial resolution of a millimeter. The reason is that what sets the spatial resolution is a gradient coil. And here we've brought another tip. If you look on the left panel, we've brought another tip with a tiny magnet on its end. It produces magnetic field gradients of 10 to the 6 Tesla per meter. And so this can define a magnetic resonance slice that has a spatial resolution of below a nanometer. So what we were able to do here was to show that we can do full 3-dimensional magnetic resonance imaging reconstruction of paramagnetic spins with a spatial resolution of better than a nanometer. But for the purpose of this talk, we are interested in strongly interacting spins. These are these magnetic waves, magnons. And for that, our spatial resolution is going to be dictated by the distance to the NB center. There are many different modalities. Scanning is just one. We have done a variety of experiments. You can have NV sitting in bulk diamond where you deposit a material of interest on top of your NV center. You can bring cantilevers that contain NV centers and position them on top of materials. The most versatile one is the scanning one that I'll be talking about today. So we're going to be interested in measuring magnons. And so magnons are fluctuating magnetization. And the question is, what is the relationship between magnetic field, which is what the NV center measures, and magnetization? So here, what you see in the bottom is a ferromagnet, all spins pointing upwards. So it's a thin, infinite film of a magnetic material. And here up, you see the NV center spin. It's a distance d away. And what we're interested in is figuring out what is the magnetic field generated by this magnet. And it might surprise you that the magnetic field generated by uniform magnetization is 0. And the reason is that you can think of each spin here as a tiny magnetic ring, tiny current ring. And when you put all these rings together, you can see that the currents inside the bulk, they all cancel. So there is basically no current flowing in the bulk of the material. And if this film is very large and and the boundaries are very far away, then the field is only coming from the boundary, and you're only going to be picking up a signal due to the boundaries, which is going to be extremely small. So we already see that the NV center, since it's measuring magnetic fields, is not going to be measuring directly magnetization, because here I have magnetization and my signal is going to be 0. What about an antiferromagnet? So here I flipped every second spin. Well, here it turns out that there is a signal, but now I suffer from this spatial resolution business. So if my distance d is larger than the separation between spins, I'm going to see a signal that's exponentially small. So here are the 2 limiting cases. So this is signal as a function of the wavelength or wave vector of magnetic texture that I have in the system. So here I have a magnon with a wave vector k. When k is 0, namely uniform magnetization, we saw the signal is 0. When k is very large, the antiferromagnetic limit, we're exponentially small. And it turns out that there is a peak in the response at around a k value corresponding to 1/d. Not surprising. By the way, the fact that the signal from k equals 0 increases linearly, as shown by this red line, suggests that what the NV center, and that's the intuition I'd like you to have, is actually measuring gradients in magnetization. So when you take a real space gradient into Fourier space, you multiply by k. And so this linear dependence here, signal is linearly dependent on k, suggests that for long wavelength magnons, we're actually measuring the gradients in magnetization. And we can do this rigorously to extract really what the magnetic response here is. So for each spin in this magnetic texture, we produce a magnetic field, and then we integrate the magnetization. It's a convolution with the response of each spin. And if we look at the Fourier space, then it's just the product of this dipolar matrix, the response due to each spin times the magnetization, but now in momentum space. And when you do this, you recover precisely the factor that we predicted before, linear in k for small k and exponentially decaying for large k. And there is more to say about this, but I'm not going to spend time doing this. Okay. So in the previous talk, we already talked about magnons. I want to say that our ability to measure magnons is interesting. It's just from a fundamental perspective, we'd like to be able to measure spin excitation, possibly the spin superfluidity. And magnons, just like any other particles, are
magnon scattering processes are very strong. Yeah.
Professor Yacoby, your sound is weird. Okay. It's normal now.
Okay, sorry. So we talked about interesting excitations, magnetic excitations, like in spin liquids, magnons, and superfluids. I just want to point out that there is also a hydrodynamic regime for magnons. So you probably heard about hydrodynamics of, definitely of fluids like aerodynamics, but there is hydrodynamics of electrons, which basically suggests that the strong interactions between electrons lead to conservation of energy and momentum. And so the center of mass of the system conserves energy and momentum, and this leads to interesting behavior of the system. Well, magnons also interact strongly, which means that they can exchange energy and momentum, but that energy and momentum still stays within the magnonic system. And here is an interesting prediction from Eugene Demler's group, suggesting that there should be a magnonic hydrodynamic mode that one should perhaps be able to detect in such magnonic systems. And this would be an interesting application of our ability to measure these magnons. So I'd like to convince you, first of all, that we can detect signatures of these magnons. And first, it's going to be thermal magnons and their relation to superfluidity in Bose-Einstein condensation, and then the full Magnon scattering platform. So we talked already about spin superfluidity, and it sounds like a very new topic, but in fact, it's a topic that's 51 years old. So this is a seminal paper from Halperin and Hohenberg from 1969, where they write a paper on hydrodynamic theory of spin waves. The first sentence in the abstract reads, a hydrodynamic theory of spin waves is developed for certain magnetic systems in analogy with the derivation of two fluid hydrodynamics for liquid helium. So basically what they show is that there is a perfect analogy for certain magnetic systems between superfluidity in helium, for example, and spin. And the intuition is actually quite simple. So if I want to compare a superfluid, we know that a superfluid breaks gauge symmetry spontaneously, and it develops an order parameter that has an amplitude, which could be complex, and a phase. And we know that gradients of the phase of the order parameter corresponds to supercurrent of helium. Similarly, if you think of a magnet below its Curie temperature, and suppose I think of a thin magnet, and its magnetization wants to be in the plane. And so when I cross over below the Curie temperature, the system develops a magnetization. But if there is no anisotropy, that magnetization can be pointing in any direction in space. And so it has an amplitude m, which is the magnitude of the magnetization, and a phase, which is spontaneously chosen. And similarly, what Halperin and Hohenberg show is that gradients of this phase, of this magnetization, would correspond to a spin current that now could propagate over and live over very extended distances. And this theory applied in the seminal theory to isotropic ferromagnets and antiferromagnets, and to planar ferromagnets and antiferromagnets. So I just remind you, we're going to be talking about a thin slab of magnet. Magnetization will want to be in the plane. Remember that if there is an anisotropy, like an external magnetic field, the spin excitation spectrum will have a gap. And this gap is shown here by the Kittel law, by the blue line. So as we increase magnetic field, the spin gap excitation increases. Above this gap, we have the possibility of exciting magnons, and they have an energy versus momentum spectrum here chosen to be parabolic. Note here that this spin gap as a function of magnetic field is no longer linear, because in this system, unlike the quantum Hall ferromagnets, the intrinsic magnetization matters, and therefore this is not a linear dependence, but has this square root dependence that is very characteristic. So how can we detect the spin gap, first of all, and the signatures of thermal magnons? So what I'm plotting here is the signature that we observe with our NV center. Essentially, it's fluorescence. So we initialize it in the ground state. And we choose a magnetic field and we scan the frequency, just like we did before for doing an ESR measurement. The bright line shown here with the ESR label is precisely the condition as a function of magnetic field where our frequency matches the transition from the ms equals 0 state to the ms equals -1 state. So this is just coherent drive of the NV center directly. So we have some external RF source and we're driving our spin, and we can see the ESR signal here. But we also pick up a signal over this dashed blue line, which is labeled FMR, ferromagnetic resonance. Ferromagnetic resonance is the resonance corresponding to K equals 0 excitations of the magnet. Now this is peculiar. We're exciting at a frequency that the NV center should not be sensitive to. It's only sensitive to its ESR frequency, and yet we pick up a signal. So what's happening here is that we're exciting the magnet at this ferromagnetic resonance. We're pumping a lot of long wavelength magnons. These are eventually thermalizing. The thermalization creates magnons that also occupy frequencies at the ESR frequency, and this gives rise to a reduction in fluorescence. So the fact that we see a signal at the ferromagnetic resonance means that we're generating magnons at one frequency, they're thermalizing to produce magnons at the frequency that we can detect them, and that's what we're picking up. So how can we use this to say something about the magnet itself? Well, first of all, we can map out the ferromagnetic resonance very clearly. You see it here, and it agrees very nicely with the Kittel law. But second, we'd like to extract something more. We'd ideally like to extract the chemical potential of these magnons, and the reason is that one kind of real signature of a Bose-Einstein condensate is that as you increase the number of particles in the system, n, the chemical potential will increase, but eventually will be pinned at the bottom of the band, because at that point we will have a large occupation of magnons occupying the ground state. And so if we could extract this chemical potential and see that it flattens out and saturates, this will be a strong signature, or at least a telltale suggesting that this system has a large occupation of the lower energy excitation. It turns out, and I'm not going to go into all the details of how this is done, but it turns out that the chemical potential can be extracted precisely from the signal that we detect at the FMR. Because it's basically, we're exciting at the FMR, but we are detecting magnons at a high frequency. That's at the frequency of the ESR. And it turns out that if we compare the lifetime of the NV center in thermal equilibrium when we're not pumping, and when we are pumping, using this very simple formula containing only 3 values that we know precisely, the omega ESR we measure directly, it's basically the spin resonance excitation of the NV center itself. We have the rate of relaxation of the NV center without pumping any magnons, and we have the rate with pumping, which is shown here. And if we use this relationship, we extract the chemical potential of magnons in this magnetic insulator. And what you see here in this color plot is a vertical axis corresponding to the chemical potential in gigahertz. And then to the left is the axis of magnetic field. And to the right is how strong we pump. And what you see is that regardless of what value of magnetic field we choose, as we pump, you see that the chemical potential rises and then it saturates. And the nice thing is that it saturates precisely at the value of the ferromagnetic resonance. And the reason is that at that point, the chemical potential hits the bottom of the band and we start getting macroscopic occupation. Regardless of what the magnetic field is, it always saturates very nicely at the ferromagnetic resonance, suggesting that this notion of a Bose condensation is really taking place.
Dr. Yacoby, there is another question from Jonathan Keep. So he's asking what's happening in the region around 1 to 1.5 gigahertz and low field. I'll go one click back. Right. Yeah. So I guess he's asking those
between okay. I will talk about this just now.
Okay.
Yeah. You see, there actually, it looks like there are ghost images of the ferromagnetic resonance, and I will talk precisely about this right now.
Thank you.
Okay. So far we saw that we can detect thermal magnons, but can we actually generate and detect coherent magnons? So how would we go about doing that? So first of all, a few additional details about the thermal magnons. So the way we're generating our magnons is using some current strip shown here in yellow in the upper right corner. The current is generating time-varying magnetic field that's driving the magnet. And these magnons are then propagating, and somewhere far away, we have our NV center, and it's measuring the properties there. So now let's look at this dispersion for a minute. So what I'm showing in the middle plot here is, first of all, the ferromagnetic resonance as a function of magnetic field, this kind of square root dependence. On top of it, I'm also showing the ESR lines for the transition of the NV center from 0 to -1 and 0 to +1. Note that at large magnetic fields, when the ESR transition of 0 to -1 goes below the ferromagnetic resonance, we don't see any signal anymore, right? This happened, you see that once the ESR line crosses the ferromagnetic resonance, we can't see anything anymore. And the reason is that under these conditions, the NV center is sensing in the gap, and there are no magnons in the gap. So that's a very nice confirmation. But suppose we choose a magnetic field like 0.02 Tesla. The ferromagnetic resonance corresponds to the bottom of the band. But if we drive the system far away from where the NV center is, but we drive it at the ESR frequency, which is this red horizontal line, this corresponds to a particular energy given by the difference between the blue and red line. And it corresponds, therefore, depending on what the dispersion is, to a finite K. So if we were to excite, so if we now focus not on the ferromagnetic resonance signal, but actually on the bright line here. But remember, our NV center is very, very far away from our drive. So it's not picking up the magnetic field generated by the current. It's only picking up magnetic fields in the magnet. You still see a very bright signal. And what this bright signal corresponds to is the excitation of a magnon with a finite energy and finite momentum as defined by this dispersion. So precisely at this point here, at 0.02 Tesla, we're exciting magnons that have a energy given by the separation between the blue and red line, and they have a wave vector that's dictated by this dispersion here of the magnons. Remember, our ability to detect magnons of different wavelengths has this shape, this filter function. It goes to 0 both at k = 0 and exponentially large. So k = 0 corresponds to the green line here. We're going to see 0. It's going to peak, and then at large k, as we move more and more to the left, it's going to vanish again. And note, this is precisely what we see here. The bright line, and I'm showing a schematic of this intensity along the bright line, the ESR line. You see it goes to 0 at the ferromagnetic resonance, it peaks, and then it decays exponentially. And in fact, this peaking value depends on D. So if we just pull away our NV centers, we move it up. So this was collected at 1 micron above the surface. If we go to 2 microns, we see that the peak becomes at a smaller value of K. And if we go to further it moves even further. So it's all very consistent with this idea that along this line, we're exciting well-defined energy and momentum, but we're not resolving this specific energy and momentum yet. Okay, so I just want to remind you now of our goal. Our goal is to realize this platform, and in fact, on YIG, we've created this yellow strip line which can drive magnons in the YIG. We have our NV center, we have a target, and the target that we're interested in is going to be another magnet, permalloy. So it's just a different type of magnet. And you see this loop antenna here that I'll talk about in just a bit. So for now, ignore it. So if we look very carefully now with this straight and rectangular strip line that excites Magnon, and we look at the ESR line, so it's the same measurement as before, only now the colors are yellow and blue rather than yellow and red. And look at this ESR line here. Note that the intensity is oscillating. I'm going to show a cut along this line. The blue line here shows this filter function, the fact that it goes to 0 when k is 0 and is exponentially dying far away. But along it, we see oscillations. And the reason there are oscillations is that our magnetic strip line is rectangular. And when we send a current through this strip line, it's generating magnetic fields whose spatial extent are given by the Fourier transform of the shape of this antenna. And since it's square, the Fourier transform is a sine k over k. And so there are values of k that are given by 1 over the width of this strip line, the yellow strip line, that we cannot excite. And that's the oscillations. And here you can see a line cut of these oscillations along this ESR line, which correspond very nicely to the size, 1 over the size of this strip line. I don't want to go too much into detail, just to show you that everything, agrees very well with the notion of being able to excite well-defined K and well-defined energy. The energy is set by the frequency and the K is set by the dispersion. Okay, so we are now exciting these magnons. We think we're exciting magnons with a well-defined omega, shown here in the bottom left formula, omega and K. And these are propagating waves. So at any given point, as we change X, this phase here, IKX, is varying, and this is very important. So we'd like to measure these magnons, and we'd like to measure the spatial extent and see that we can observe propagating magnons. So one thing to note is that if we sit along this ESR line here, we can see that if we drive for longer and longer time, we can see that the NV center response is oscillating. These are precisely Rabi oscillations. So what the magnons are doing, they're a time-dependent magnetic field. And if you look at a two-level system in a rotating frame, a time-dependent magnetic field oscillates perpendicular to the quantizing axis and causes driven oscillations in the rotating frame. So if we wanted to detect this phase factor, so basically what I'm saying is that we prepare our system in the 0 state along the North Pole. Our magnons are an AC magnetic field that drives the system from the North Pole to the South Pole. And the phase here, this e to the ikx, that chooses the direction in which the system rotates. And so the precise axis along which the system rotates. And so if we want to determine this phase, what we're doing is we're adding another reference antenna, which is this loop here. This loop produces a magnetic field that's uniform in space. And so it itself cannot drive magnons because its frequency is not matching to the k equals 0 magnon, but it can contribute to driving the NV center. And so the total AC drive is given by our reference phase and the magnon, whose angle here, B magnon, depends on the location, IKX. And you see that we can generate constructive and destructive interference between the magnon field and the reference field that would allow us to determine this specific phase, IKX. So this is what you're seeing in the bottom right corner here. You see, these are images, snapshots of propagating magnons. Each frame here corresponds to a fixed reference phase. And at that reference phase, we can see the constructive and destructive interference of the signal such that we're causing driving of the NV, not driving, driving, not driving. And the separation between these wavefronts in real space is precisely the wavelength of the magnons. When we vary the reference phase, we shift the condition under which we pick out this IKX. And so we can really pick out the precise phase of this propagating wavefront in real space. So this is a nice achievement here where we can image in real space propagating magnons. I want to emphasize these are not standing waves, they're propagating magnons, and we can pick up the wavefronts of these propagating magnons by locking onto a particular phase of this propagating magnon, to this IKX. Once we can see these magnons in real space, we can now extract immediately their dispersion, because we can just change the drive frequency and then see what is the wavelength. So here, for example, before this image, you can see that the wavelength is about 4 or 3 microns. Here, the wavelength is already 400 nanometers, and we can go down even below that and extract what the frequency is as a function of momentum of these magnons. And this is the blue line is the theory for the Magnon dispersion in this thin film, and the dots are our measurements. Okay, so far we have shown that we can image not only the amplitude but also the phase of the magnons, the propagating magnons. We can change the energy and momentum, so we have a coherent source of magnons, and now we can do a scattering experiment. So in order to determine both amplitude and phase, we need to do 2 measurements. So the first measurement we're doing is we're turning off our reference antenna. So what's happening is that we're only launching magnons. These magnons hit the target, and in the bottom right panel, you see a white circle. That's our target. And you see that the intensity that we pick out, so we have a coherent magnons. The target itself responds to these magnons and sends out its own magnons. And these interfere to produce intensity variations that are shown in the bottom right panel. So this we call an amplitude image. We can now do a second experiment where we now turn on the reference antenna, where now, in addition to the interference of the incoming magnons, the scattered magnons, we have also our reference phase that now allows us to see the phase of the wavefronts. And this is our phase image. And we're going to use these 2 images to try and reconstruct the properties of the target. So up to now, I've avoided using any formulas. So now I'm going to use just a few formulas to give you a sense of what is it that we expect for the target. So give you a little bit of intuition of what happens. So we have a magnetic field that we're detecting, H. There is a magnetization in the system that's given by the underlying magnetization and a fluctuating part. So since we're mostly interested in the response of the system to the magnons, we're only going to be looking at a component that is oscillating at the frequency that we're exciting. So h e to the minus I omega t and the corresponding magnetization m e to the minus I omega t. One could show that at the frequencies we're working at, the magnetostatic Maxwell equation approximation hold, which means that this requires that the wavelength of light at the frequencies that we're working in vacuum is much, much larger than the wavelength of the excitations that we're considering here in the medium. And so in the medium, we have magnons in response to Maxwell's equations. In vacuum, this is just going to be light. The wavelength of light at gigahertz frequencies is centimeters, and in the medium, it's microns. So this approximation holds very well. And effectively, it says that we can ignore the electric fields in the problem. So under these assumptions, what we know is that the curl of the magnetic field or magnetic induction is 0, and the divergence of H plus M is 0. And our magnetization of our target is a static magnetization, but we're not interested in the static magnetization. We're interested in how that magnetization responds to the magnons that we're sending. So there is a delta M target. Now the curl of H equals 0 suggests that we can write H, we can derive it from a scalar function psi. And if we plug that into the second equation, we get a Laplace equation with a source. And the source is given by a divergence of the fluctuating component of magnetization. So if you were to think that this source was a delta function, then basically we need to solve and find out what the Green's function of psi is. And that Green's function is given by the dispersion itself, by the response of the medium. And then we need to add a lot of these delta functions to construct our target such that it fits our scattering amplitudes. So let's see what our target looks like for our magnetized disk. So this is M0. So this is the magnetization of the disk in the absence of any magnons. When the magnons are there, this magnetization is going to fluctuate at the frequency omega. Since it's magnetized along X, changes in the magnetization of M0 are going to only be along Y. It's only going to be moving perpendicular to the magnetization because it's already fully magnetized in X. So that's delta M. And our target, you see, is the divergence of delta M, which is going to give us a positive signal on the top and a negative signal on the bottom. It's going to look like a dipole. So that's the intuition for why you'll see that we end up with dipoles. So this is just the last slide. And I want to show here on the left are the measurements. And you see they're very, very detailed. We see a very nice scattering platform, scattering amplitude on the top left, and the phase image on the bottom left. It shows a lot of details. This is the measurement. And on the right is our attempt to construct a target and to use what we know about the Green's function for this system in order to mimic the same response. And so in the insets in the middle panel, you see the real and imaginary components of our target, which looks like a dipole. It's positive on the upper side and negative on the bottom side for the real and the imaginary. And you see that it produces something that looks a little bit like the target, but not really, but by the real measurement. The phase looks a little bit better, which is panel F. If we add the next moment, so not only a dipole, if we add also a quadrupole, you see that we can improve the amplitude and phase image to match better our measurement, but it's still not perfect. But this is how far we've gone at the moment. So what you see here is a forward process where we basically suggest a target, we compute what the scattering results would be for that target, an amplitude and phase, and we compare and we minimize as we're kind of slowly varying the parameters of the target. In principle, because we're measuring both amplitude and phase, we should be able to take directly our measurements. And the important thing is that we don't need to take our measurements where the target is, where you see this flowery shape. We can take it only far away from the target. And in principle, we should be able to reconstruct our target just going from the measurement to the source. But this turns out to be very, very difficult. So for now, we're doing the reverse. We're suggesting a source. We're calculating what the results should be. And we're trying to match our measurement with the simulation. But this turns out to be not so simple. You can easily see that the measurements contain more details. And we suspect that what's happening is that our model that we're generating based on the source is missing some components. So we're going to have to add physics components in order to realize an agreement, a better agreement, even though this is already not so bad, but we would want to get a better agreement between our simulation and our measurement. So with this, let me pause here and just again acknowledge the contribution of many collaborators. This last part was done in collaboration also with Eugene Demler, Ilya and Driss, who've helped us a lot in modeling the response of this magnet and the reconstruction of our scattering amplitude and phase plots. for this Magnon scattering platform. And with this, I'll stop and take some questions.
Thank you. The data was very beautiful. So the first question which was asked during the talk by Samer asked, what you mentioned that the relaxometer can be used to detect in the gigahertz regime. Can this be pushed to the terahertz regime to probe, for example, antiferromagnets?
Yes, so in relaxation mode, yes. The problem is that, you know, the way the NV center works is that when you want to measure a particular frequency, you dial in a magnetic field such that the level spacing of the NV center corresponds to that frequency. So if you wanted to go to, let's say, 1 terahertz corresponds to about 35 Tesla. So I think your antiferromagnet at that point might already be very different from what you wanted to study. So it's kind of it's not ideal in that when you want to change frequency, you need to apply a very large magnetic field in this particular system. So I doubt that it would be useful, but maybe in certain cases it would.
Thank you. Question from Grace Pan. How about spin fluctuation spectra in, say, platforms without nominal magnetic order, such as doped cuprates, spin liquids, and etc.?
Absolutely. So this is a direction that we're very, very interested in. We've had some attempts, failed attempts, to try to measure spin fluctuations in ruthenium trichloride. So yes, I think absolutely. I think this is one of the key motivations that we had in developing a lot of these techniques, is to measure spin fluctuations in these interesting materials where electrical techniques don't work. There are, of course, for every technique, there are limitations and one needs to address the details, but yes, we are very interested both in the pairing, you know, if the pairing mechanism, let's say in the cuprates involves magnetic interactions, then these might lead to spin fluctuations. One needs to be careful if you're trying to do this in the superconducting phase, then the system has a lot of other magnetic response that has to do with the superfluid response. But yes, and spin liquids, as I mentioned already, very interesting. So yes, I think this is very interesting directions. I wouldn't say they're easy, but they're very interesting.
Okay, thank you. Question from Chunli Huang. What's the smallest wave vector you can excite with this method?
So in principle, I think we can easily go down below 100 nanometers. Whether we can get down to 10 is not so easy. What happens is if the system if you want to go down to very short wavelength, you will need to use a magnetic slab that has a very small thickness. So typically, the kind of the hand waving argument would be that the lowest wavelength you can excite is going to be the film thickness. In our case, we've been using 100 nanometer film thickness. So if you wanted to use, and you know, YIG shows very good properties even when you go down to 10 or 20 nanometers. So I think this is possible to go down to these wavelengths, but it does require a very thin slab YIG.
Mm-hmm. Another question from also Chunli Huang. During the reconstruction, did you use a 2D or 3D grain function?
Yeah, so our everything is two-dimensional. So our YIG is two-dimensional, and in fact, the magnetic excitations of YIG are what's called surface magnons. So they reside on the top surface of this film, and they decay exponentially into the bulk. These magnons are very strongly interacting with anything you put on the surface. That's why we're using those. And so there is very little content in the vertical direction. Our target is also a very thin slab of permalloy. So again, two-dimensional. By the way, I didn't have time to show this, but we've now done experiments with different targets. So we can replace the target. For example, we put a metallic target like copper, and the scattering patterns are very, very different. And the response, so there is nothing magnetic in copper. And the only reason it responds to the magnons is that the time-varying magnetic fields associated with the magnons are driving currents through the induced EMF in the copper, and these then generates current that generate magnetic fields again. So it's kind of an interesting response, and I think it's still an open theoretical question, what precisely is the structure factor of magnons interacting with various materials. So I think this is something that will kind of be revealed over the course of the next months or years.
Next question is, can you discuss about the energy of these Magnon modes?
Yes, so I've shown mostly dispersions that are quadratic. This is not correct for the surface plasmons. In fact, the surface plasmon dispersion is, it starts from the spin gap, and as you go to larger and larger K values, it starts quadratically, but then it saturates exponentially. So this is a big advantage because it means that we can choose wave vectors over a very broad range of values without actually needing to go to very large frequencies, which is problematic, as we talked about for the NB centers.
Okay. Next question by Joshua House. In certain weak itinerant ferromagnets, a new gapped mode, Higgs or amplitude mode, has been seen, which is distinct from the magnons. Will you be able to measure or detect such a mode?
I hope so. I am not very familiar with this. So if you want to send me an email with a link or something like that to that, I would be happy to take a look. I'm always looking to see new interesting directions to apply some of these techniques. So yeah, please send me an email with more details.
Sure. The next question is, wouldn't limit spatial resolution limit the applicability of the NV technique to antiferromagnets, where spin direction may change on the angstrom length scale?
Yes, I think that currently we don't have really good ideas of how to detect antiferromagnetic spin excitations. However, many of the antiferromagnets, when you subject them to some magnetic field, they can't. And so then they do have some ferromagnetic modes as well. I think these we might be able to detect. But you're right, things that have wavelengths on the order of a few angstroms, we should not, it's going to be very, very hard to detect them because typical distance between our NV center and the magnetic material is, at best, maybe, let's say 10 nanometers. We might even be able to go a little bit below, but it's an exponential decay. So, from 3 angstroms to 3 nanometers, it's going to be a big, big suppression.
Next question is how to excite only positive K, not negative K in the propagating wave experiment. I guess, yeah, we'll see wave in one direction.
Well, okay, so this is actually interesting. So first of all, even if there were negative K propagating modes, we would be able to see them, and we could then image the pattern both forward-looking and backwards. The interesting thing about these surface magnons is, the breaking of time reversal symmetry actually causes them to be chiral. So it turns out that magnons on the top surface are only propagating to the right at a given magnetic field, and the ones that propagate on the left, they live on the bottom surface. So there is a separation between the forward and backward moving magnons, specifically these surface magnons. There are also bulk magnons that one could work with, and these would be propagating both forward and backwards.
Okay. Maybe probably the last question of today, since we're already at the time. Is it possible to detect the antiferromagnetic spin wave?
Yeah, so as I said, I think it really depends. If you have, for example, tantalum sulfide, I believe, which is a candidate spin liquid, has the Star of David type of arrangement. And so the unit cell there might be, you know, a couple of nanometers. If the problem is the wavelength. So we will not be able to detect things that have a wavelength that's, let's say, shorter than 10 nanometers. So this is a limitation of this technique, and currently we don't have a solution for that.
Yeah. Okay, thank you. Thank you, Professor Amir Yacoby, for the wonderful 2 talks. And we'll proceed to our poster sessions. And yeah, stay here for the posters. I will hand it now to Xiaoyu to moderate the poster session. Thank you.
Well, thank you for having me.